Hello, everyone. Thank you for joining us today. We are the In Situ Resource Utilization Team. Our project, abbreviated as LEMUR, stands for Lunar Exploration Mission using Regolith. Let's introduce the team.
Hello, my name is Jatin and I'm from Texas.
Hi, my name is Pia and I'm from California.
I'm Molly and I'm from Maine.
I'm Thomas from Louisiana.
Hello, I'm Serena and I'm from Missouri.
And I'm Divya, and I'm from Michigan.
This is our team's mission patch. It shows the moon because that is the location of our mission, and the area we drew is Shackleton Crater, a potential landing site for the Artemis program. The sun represents the solar power collection that powers LEMUR. Each of the 7 sun rays represents a different team member, including our mentor, Miss Hanover, and our last names are all written along the bottom. In the center of the crater sits a toboggan with a lemur tail, because our project name is LEMUR, which represents the pulley system that pulls the toboggan in and out of the crater.
Let's start with some background information. In situ resource utilization, or ISRU, refers to using materials found on site rather than importing them from external locations, in this case being the Earth. This approach is important because of the high cost of launching materials to space. Currently, sending 1 pound of material to the moon costs about $10,000. By utilizing lunar resources, we can significantly reduce these costs and the dependency on supplies from Earth. Two of the most abundant resources on the moon are ice and regolith. Ice is found in great amounts in permanently shattered regions and can be processed to provide resources essential for supporting human life. Lunar regolith, the loose layer of dust and rock covering the moon's surface, is another vital resource. Not only can it be used for construction and manufacturing, but it also effectively blocks harmful solar radiation, offering protection for habitats and equipment. In this project, we use regolith for manufacturing vehicles. Using its ISRU techniques allows us to harness these local resources, making lunar exploration more sustainable and cost-effective. We aim to explore the southern region of the moon, particularly the permanently shadowed areas of Shackleton Crater at the lunar South Pole, which is of great interest due to its potential ice deposits. This area hasn't been extensively investigated before, but missions like Viper and Artemis are set to explore it soon. Viper, part of NASA's Artemis program, will search for ice and other volatiles in this region. However, Viper could face challenges with sinking into the low-density regolith found in these areas. To address these challenges, our project proposes using a toboggan-type vehicle, similar to a flat-bottom sled, which is more practical for navigating the fine-grained regolith and steeper slopes compared to conventional rovers. This approach is not only suitable for the terrain, but also easier to construct from moon resources, aligning with the goals of Artemis to develop sustainable exploration solutions.
Shackleton Crater has regions of both permanent darkness and almost year-round light. 3 points on the rim of the crater remain in constant sunlight for over 90% of the year. These spots could be utilized for rover resting and recharging through solar energy or future Artemis base camps. The reason that everywhere around the world gets exposed to sunlight during the year is due to Earth's axial tilt of 23.5 degrees. As the Earth orbits the sun, this tilt causes different parts of the Earth to receive varying amounts of sunlight at different times of the year. This axial tilt is responsible for the changing seasons and ensures that over the course of a year, every location on Earth experiences periods of daylight and darkness. The moon has a much smaller axial tilt compared to the Earth, and it has deep craters, some more than 2 miles deep, double the depth of the Grand Canyon. Because of this smaller tilt and deeper craters, some areas of the moon, especially those in the southern pole, are in perpetual darkness. Focusing on the southern pole of the Earth, this region experiences areas of perpetual darkness during the winter months. The Earth's axial tilt prevents sunlight from reaching the southern pole, causing the sun to never rise above the horizon and leading to continuous darkness for several weeks in certain areas. Because of the very steep slopes of the crater's rims being around 30 degrees, typical rovers are not able to traverse down into the permanently shadowed regions of Shackleton. Rather, they would explore smaller, less deep, and wide craters in the surrounding area. For example, the Viper rover, a NASA moon rover, can only traverse slopes of up to plus or minus 15 degrees, which makes it impossible for the rover to observe and traverse the large Shackleton crater. But due to our design using a pulley system and a toboggan-type vehicle, our rover would theoretically be able to travel to the bottom of the crater and explore the potential abundance of water ice and valuable materials in the regolith, such as metals including iron and aluminum. Because Shackleton Crater is so deep and in permanent darkness, the bottom of the crater reaches temperatures of 40 degrees above absolute zero. In other words, negative 388 degrees Fahrenheit. In order for electrical components to work, they typically need internal temperatures of warmer than negative 58 degrees Fahrenheit. much higher than the temperature of the crater. This calls for the need to maintain a high internal temperature, something that also uses energy. The most productive source of energy on the moon is solar energy, as it is much more efficient in space and on the moon than it is on Earth due to the absence of a thick atmosphere. In order to utilize the best light to energy conversion ratio possible, a solar array located on the rim of the crater in the almost year round light will be on a tilting axis to be perpendicular to the angle of the sun, normally around 15 degrees. Then, using microwaves, a wireless power transfer to the receiver on the transporter will be completed in order to power tools and keep the electronics warm. Additionally, the solar array system will be equipped with tracking technology to ensure optimal alignment with the sun throughout the lunar day. This precise alignment is crucial for maximizing energy capture and efficiency. The energy collected will then be stored in high capacity batteries to provide a consistent power supply, even during periods when the sun is not directly overhead. Furthermore, the implementation of wireless power transfer via microwaves not only reduces the need for large quantities of cables, something very expensive to launch, but also allows for greater flexibility in positioning and mobility of the vehicle. This approach ensures that our vehicle can explore the depths of Shackleton Crater without being tethered, significantly enhancing its operational range and efficiency.
Our mission objectives are to design a device that can travel to the bottom of Shackleton Crater and collect resources, to employ in situ resource utilization techniques to prove whether or not it is possible to use lunar regolith to build structures and other apparatuses, and to investigate ways to use solar energy to power devices on the moon. Now for our brainstorming process. Our proposal for utilizing ISRU techniques on the moon is to create a vehicle similar to a toboggan, with a flat bottom and no wheels, curved ends that point upwards like a canoe, and ample space in the interior for carrying materials and instruments. The toboggan will be a better vehicle for traversing the moon's terrain than a traditional wheeled rover. The issue of low-density regolith causing wheels to sink is combated by the flat bottom of the toboggan, which would smoothly glide over the lunar surface. Furthermore, the high walls of our vehicle protect the instruments and materials inside from the dust being kicked up by the toboggan moving over it. Before moving on to the hands-on experimental part of our project, we discussed how the toboggan would explore craters. We would use a winch to anchor the toboggan to the rim of a crater and slowly lower it using a pulley system. Our vehicle would have various places to attach scientific instruments, measurement devices, and cameras, all of which would be sent to the moon from Earth and be charged on the moon via solar energy. Now I'll explain how we harness ISRU techniques in our proposal. The toboggan itself will be made from a clay-like mixture of lunar regolith and water, both of which are resources already found on the moon. We actually experimented with this to determine what type of regolith and how much water is ideal for the sturdiest vehicle, which we will get to soon. Once molded into the shape of the toboggan, the mixture will be left in the cold shade to harden, and when it is fully solid, the scientific instruments and solar panels can be attached. Now we'll explain our experiments in building prototype toboggans and testing them. We started by testing several different toboggan designs by making them out of scrap paper, and we ended up choosing an origami canoe design. The reason we specifically chose this origami design is because it had a flat bottom and pointed ends, which is exactly what we wanted our toboggan to look like, because this allows it to smoothly traverse across the lunar surface. Also, having an origami design would allow humans on lunar missions to just take some square aluminum sheets with them and then assemble the toboggan mold upon landing on the moon. We then cut out the flat bottoms of some aluminum food trays and used the same origami design to shape them into toboggans as well. The reason we chose to use the aluminum trays for the molds is because they're strong and sturdy, yet still flexible enough to shape into a mold. These molds can be reused a number of times to make multiple regolith toboggans. We made 2 identical versions of this mold which were the same size and mass.
Next, after we had the molds, we started making the actual toboggan prototypes. We used 2 different types of lunar regolith simulant in order to test which one made a stronger toboggan. We used simulants of Mare regolith, which is mainly composed of basalt, and Highlands regolith, which is mainly composed of anorthosite. Both of these types of regolith are present in abundance at our chosen location of the South Pole, although there is slightly more anorthosite. One of the initial observations that we had about the regolith is that the Mare regolith simulant was much coarser, while the Highlands regolith was finer. So for each of the 2 types of regolith, we mixed regolith with water until the mixture reached a clay-like consistency. This process did take a little bit of trial and error, and after that we poured the mixtures into the molds and shaped the insides to get a canoe-like shape. After that, we put them in the freezer overnight at around 0 degrees Fahrenheit or negative 18 degrees Celsius. We made sure that both toboggan prototypes were about the same mass to ensure that we would be able to accurately test them. Here's a quick time lapse featuring Pia and myself that shows our process of making the toboggans. After we took the toboggans out of the freezer the next day, we proceeded to run a series of tests on them to determine which type of regolith made a stronger toboggan. When we're on the moon, it's important that the toboggan is able to travel across the lunar surface as smoothly as possible, and also be able to efficiently traverse across steep environments, such as craters. So that's why the first test that we ran was a sliding test. In this test, we simulated a slope by placing a tray full of regolith at a 25-degree angle using some tape rolls, which you can see in the photo here. We tested both toboggans by manually sliding them through the slope of regolith and seeing which one slid more easily. The next test we ran was a carrying test, where we placed 3 objects of 3 different masses inside of each toboggan. We had one 75-gram object, which is the smaller measuring tape that you can see at the top of this photo, one 157-gram object, which is the larger measuring tape in the middle, and one 232-gram object, which is the stone at the very bottom. Now we're going to discuss the results of our experiments, as well as our overall conclusions. When we did the sliding test, we found that the toboggan made out of Highlands regolith was much easier to slide than the toboggan made out of Mare regolith. Here you can also see the results of our carrying test. As you can see, the toboggan made out of Mare regolith, which is the black one at the top, crumbled a lot more after the carrying test than the toboggan made out of Highlands regolith, which is the light gray one at the bottom. This is likely because of the fact that if we go back to our initial observations about each type of regolith, the Mare regolith is more coarse in general, and the grains are larger. In contrast, the Highlands regolith is much finer. So this could be why the Highlands toboggan didn't crumble quite as fast. We decided that the Highlands regolith was a better option for building items out of. Firstly, the Highlands toboggan was much easier to slide than the Mare toboggan, and as mentioned earlier, it's really important that the toboggan is able to slide well. And lastly, when we performed the carrying test, the Highlands toboggan did not crumble nearly as much as the Mare toboggan did, which proved that it was much more sturdy and robust.
Then we analyzed the chemical composition of common building materials on Earth and compared them to moon regolith using principal component analysis, k-means clustering, and then calculating the cosine similarity. We found that high-tide basalt was very similar to low-tide basalt, and the next similar building material was brick. On the other hand, highland regolith was a lot more similar to brick than the other 2 regoliths, indicating it is a more suitable building material. This may be because of the slight differences in chemical composition. Compared to the basalts, the highland regolith has more aluminum and less iron. We could extract more specific materials from the regolith as well, such as water, glass, and aluminum, which would help create other crucial items. Once the toboggan is built, it will help us mine and explore the moon's surface. This includes getting resources from the bottom of craters that have never been investigated before. A shovel will be attached to the toboggan to collect the regolith and other moon rock. Furthermore, we will add an ice drill to map water sources, which is very important in ISRU for colonies on the moon. Water is essential for human survival and could be used in electrolysis to separate water into oxygen and rocket fuel. We also could sample other parts of the solid moon rock and figure out what exactly makes up the moon. For that, we would use various spectrometers created by Viper, including a neutron spectrometer to detect hydrogen, a near-infrared spectrometer known as NERVIS, and a mass spectrometer known as MSOLO. This study demonstrates how ISRU can be used to create sturdy apparatuses from hardened regolith, providing an efficient, cost-effective method for developing sophisticated lunar colonies. For future lunar missions, in situ utilization of regolith can be pivotal for building colonies by extracting specific resources. The resources gathered by toboggans can be used to manufacture additional instruments, creating a sustainable and self-sufficient cycle.
We have an environmental responsibility to leave the moon and other places we visit in space the same way we found them. In order to do this, we have to make sure that we're not overmining limited resources in order to keep the composition of these other bodies the same. We also can't leave things from Earth or other planets on the moon that could have the potential to damage the environment there, because introducing certain items, materials, or organisms could have the same effect as invasive species here on Earth. While we tried to keep sustainability in mind throughout our project, it's important to find more sustainable methods in the future. Now we're going to reflect on our time here at SEAS. The SEAS program was a unique experience for all of us and allowed us to learn many new things about STEM from experts in specific fields related to our research and project work. The main challenge we faced was the limited amount of time we were given to complete the project, which led to certain aspects of it feeling rushed. Additionally, there weren't many opportunities for bonding or interacting with our team or members of other teams before we immediately jumped into work, which presented problems with team dynamics. Some of the highlights of this program were meeting and working with like-minded peers from all over the country who are all passionate about space, and speaking with mentors and experts who are knowledgeable about subjects we're interested in, though there are many more. We are very grateful for having the opportunity to participate in the SEAS program because we met many new people our age who are passionate about the same subject we are. It was a great learning experience that taught us not only about STEM but also about how to work with people we have only just met.
I'm incredibly honored to have been selected as a NASA SEAS intern. This week has been an extraordinary journey, working alongside my amazing teammates and mentors. Meeting astronauts such as Dan Tanney and mission leads like Parker Francis have been an amazing experience. I had the incredible opportunity to network, learn about microgravity, and delve into the intricacies of space exploration. The knowledge and connections I've gained are invaluable, and I'm truly grateful for this unique experience.
I am so grateful to have participated in the SEAS program and furthered my passion for space. I learned so much this week and will always cherish the memories I made here. Thank you to everyone who made this possible.
It's hard to say what my favorite part of the SEAS internship was because I had so many unforgettable experiences. One of the best parts was drawing the mission patch and doing hands-on experiments such as building the boats that helped us better visualize how our project worked.
Being selected for the NASA SEAS internship has been an absolutely great experience. Working on the in situ resource utilization team has given me hands on experience with the technology and innovative thinking needed for lunar exploration. The opportunity to collaborate with like minded peers and learn from industry experts, such as those on NASA's Viper rover team, has been incredibly inspiring. This experience has not only boosted my confidence in my skills, but has also solidified my passion for aerospace engineering and robotics.
This week at the NASA SEAS internship was incredibly rewarding. I loved meeting brilliant people from across the country, as well as our mentors, SEAS staff, and experts who spoke with us. I especially want to thank my team for their diverse perspectives and working styles. I also want to thank the mentors who woke up early to go to the gym with us. It was very interesting to learn about the moon and the Artemis mission, and this experience as a whole was awesome.
I am so unimaginably grateful to have had the opportunity to be a NASA SEAS intern. One of the things that I think is the most unique about this program is its emphasis on real world application of scientific principles. After working with my team and mentors on this project, I can definitely say that I've learned more in this short week than I have in any other week in my entire life.
So many people more experienced than us helped along the way as we navigated through each stage of SEAS and developed LEMUR into what it is now. Stephanie Hanover, our mentor, supported us every step of the way as well as facilitated team bonding, and we are so grateful to her for all that she's done for us. We would also like to thank Laura Tomlin, Selena Miller, and Margaret Baggio, as well as the rest of the NASA SEAS team, for coordinating everything, keeping us safe for the week, and assisting us with our project as well. Zoe Zeladik, a SEAS alumni, gave us a lot of tips as well about this project, the Z-Cube, and parabolic flight. Additionally, Parker Francis, a Viper rover team member and driver, spoke with us first online and later in person about our project, since the Viper and LEMUR missions overlap in many ways. He gave us so much helpful information and ideas that really helped shape our project and steer it in the right direction. Jim Heisey, an engineer at Iowa State University, also talked with us later on in our project and helped us make our last few tweaks to LEMUR and finalize the design. In addition, we have many other speakers who provided insight on various space-related topics, including Bob Twiggs, Dr. Kevin Crosby, and Dr. George Pantelos. Finally, here are our works cited. Now we'll open it up for any questions.